And so in our module, again, this lab is not due until a week from Sunday. I don't know that I've made the actual assignment yet, but I will. It's again, PDF or doc. It's lab 5. I'm going to open the PDF. Actually, I'm going to open the doc because I'm going to actually put data on here. I will say that the funny thing about this lab is it's actually easy to do the experiment. Whoever is doing the experiment of your group, or if you're doing the experiment, it's easy to do. It's kind of hard to do right. So we're going to talk about it. Let me go back to my PowerPoint for a second. We've already learned that on an inclined plane, and we're going to assume this is our IO lab sitting on the inclined plane, inclined at some angle, that the forces on it, if we turn the incline, are mg sine theta. There's a normal force, and mg cos theta. And if there's friction, there may or may not be, it'll be here and it'll be mu n. And then we're going to take the acceleration, in our case, to be down. More on that later. So we get that MA is either mg sine theta, or if there's friction, MA is mg sine theta minus mu n. In that case, we need m, n, so MAY is n minus mg cos. That's obviously 0, and n is mg cos. We know that though. So putting that in, getting rid of the m, we get that A is either g sine theta, or A is g sine theta minus mu g, move you out of the way, cos. So hopefully you're all okay with that. Now, I'm going to move to a new slide because A is g sine theta. We can use the small angle approximation, which as long as theta is about 10 or less, sine of theta is approximately theta. And cos of theta is approximately 1 minus theta. We don't need the cos one, but you can check that on your calculator by putting in sine of 10 degrees. And what do you get? Well, sine of 10 degrees, yeah, I will, Kevin, after we're done. So checking this small angle, do sine of 10 degrees. And, oh wait, I should take something back. So this works as long as we're in radians. And going from theta in degrees to theta in radians, remember that you have to convert by either 2 pi over 180, 2 pi radians over 180 degrees, or you could go 360, or you could go pi over 180 degrees. So to convert 10 degrees to radians, we multiply by pi rad over 180 degrees, and we do that really fast, and we're going to have to do that for this lab. So we get 0.1745 rad. Now, sine, if you put your calculator in radians, sine of 0.1745 radians is 0.1736. So small angle approximation works for sine. Knowing that, we can then say that A g sine theta is approximately A g theta. Okay. If now we want to find the velocity, if it starts at the top at rest, v is equal to 0, v naught, and then it reaches the bottom and we want to find v final, what is v final equal to? Well, assuming this is constant, we have v final is v initial plus at. This is important for your exam too. Remember, this is the general form. If we're talking free fall or projectile motion, a is minus g. But this is the form for any acceleration. we have an acceleration as g theta. We have that this is 0. So we get v final is g theta t. And therefore we can find g is v final over theta times t. And that will give us a experimental answer for g. And all we have to measure is the time and the velocity and the angle. So we're going to use our IOLAB. We're going to roll it down a plane. We're going to choose 4 angles, 5 degrees, 10 degrees, 20 degrees, 30 degrees. We're going to drop it from rest. So V initial will be 0. We're going to measure V final from IOLAB. And then we're going to get T, the change of T from the IOLAB. And that'll give us essentially an experimental value for G anytime we roll it down a plane. That's the whole point of this lab. Now, how do we do that? So all this stuff is the experimental stuff that I just talked about. What we need to do is we're going to take the IOLAB, put on the position and velocity. I'll do this in a minute. I'll do a couple trials for you. We're going to need, so here's the fun part of this. I'm going to use a book and some books. So I'll have just a book, a nice long book, but a book. I'm going to let it roll down that. I have a protractor that I bought from the grocery store for like 50 cents or $1. If you don't have one, you can actually print one off online, and the angle should be the same. So if you print one and cut it out, you can use one that you printed out. And then a stack of books. So I have a stack of books that I'm going to use. Basically, I'm going to put a book like this, and I'm going to find the angle on this flat book. If I adjust it, I can get a better angle, and I'm going to let the IOLAB roll down that, and I'll show you that in a second. Someone was here and left. So when we do that, what we're going to get is we're going to get 4 screen captures, and I'll show you those. We're going to fill out this data table from the IOLAB, and I will actually do that in front of you. But you're going to need to do it on your own. So this lab is a little bit of trial and error. And then I want to talk about the graph, because we're going to take these 4 data points, these 4 V and theta T, and we're going to graph them, get a slope, and that will be our experimental G. But we're also going to find it for each one. And then we'll go through the calculations in the table of results. But let's talk about getting this and then putting it into Excel. So I need to download this and open it so I can work with it. Okay, so here's my working one, and I'm coming down to here. Now, one thing on the protractor, well, 2 things. First of all, we have this plus or minus. My protractor lists only an angle. Remember that resolution is the smallest thing. So mine, the smallest it will give me is 1 degree. I need to convert my angles. My angles would be 5 degrees plus or minus a half a degree, 0.5, because that's what my protractor shows. But I can't be in degrees. I need to be in radians. So conversion is 5 times 2 pi divided by 360. So 5 degrees times 2 pi rad divided by 360 will give me 0.87 rad. 0.87 rad. And then this needs to be half a degree, which is 0.5 times 2 times pi divided by 360. 0.0087 rad. So make sure when you do this that your angles are in radians, not in degrees. So 5.87 times 2 will give me 10. This would be 1.47. Same error. So the error will be the same for each of these. I'm not going to write it each time. 20 degrees will be double that again. 3.48. That can't be right. So I think I left off a 0. 5 times 2 times pi divided by 360. Yeah, I left off a 0 here. Whoops. I'm like, that is way too big. So this would be 0.147 times 2 is 0. Is that right? 0.087 times 2 is 1.74. I'm dyslexic sometimes. And 0.174 times 2 is 348. And then I need 30 times 2 pi divided by 360 is 0.5236. 0.5236. And they all have the same, so they all have the same error because they're all done with the same protractor that has the same resolution of 1 degree. What I've done though is I've converted using 2 pi rad over 360 degrees to convert my 5 degrees, 10 degrees, 20 degrees, 30 degrees to radians. Now, here's the hard part though. So most protractors have like a little circle right in the center, and that has to be the level ground. My book that I'm using is kind of thick. So if I want to find the angle, if it's at some angle, I have to make sure that the center of that circle is at the edge. And so this would be 5 degrees, 10 degrees. That is a little hard to do. It's a bit of a pain, just so you know. But it can be done easily. And just make sure, I believe that's about 5. Maybe I'll take this off. So I'm measuring out to 5 degrees, which is a huge, and I know you guys can't see it, but and this is not going to be, it's too bad. So what I would do, and hopefully you can see this, what I would do, I know you can't see this, but I have 2 books like this laying on the table. I have this enough, and then I'm checking the angle of this book to make sure it's 5 degrees to the tabletop. You got to make sure everything's kind of level and make sure that you're at 5 degrees. And that's the part that makes this hard, but we'll check it when we get our data. Turn on your iLab. Start your software first. Turn on your iLab, and then just take it, set it on the book, and drop it and let it roll down. When you let it roll down, catch it with your hand, but drop it from rest. I really need to stop picking up this book. Here's the fun. So this is at 5 degrees. Turn on wheel. We don't need acceleration. Hit record, set it on there. Make sure it's all zeroed out, nice, and stop it. So from this, and make sure that you run it down with the eye bolt up so that when it runs down, it'll be positive. If it's negative, it's okay, just flip the sign. But notice, if I zoom in here, I can see that my position went from 0 to like 19 inches or 19 centimeters. And my velocity went from 0 to 0.468. So we need to do 2 things. Highlight the data from when the velocity starts to change until it stops, when you stopped it with your hand. Get the velocity at the peak, 0.460 for me. Why do I have 2 of these open? So this one would be 0.460 meters per second. What is the plus minus? Remember that our resolution on the iLab is basically the last digit here. So for the velocity, it's 0.001, half of that is 0.0005. So this would be plus or minus 0.0005 meters per second. My time, which is why I grab this interval, I can see my time interval is 70000. So 0.7 seconds, 0.7000. I believe it does 5, right? 1, 2, 3, 4. Yep, 5. So this is plus or minus half of that last digit, which is 0.0000. That's 5. So 6. 5 times 10 to the minus 6. Now, I also need to write theta times time and make sure theta is in rads. So 0.087 times 0.7 is 0.087 times 0.7 is 0.0609. We're going to do that for each one of these. So bear with me. I'll try to go fast. And then also grab a screen grab of this with the highlighted section. Just grab on Mac, it's Shift Command 5. On Windows, there's a sniping tool or a print screen that'll let you do it. I want one for each of the degrees, so maybe name the file degree if you can, but it's okay. Put like a little label on which one they are, although it's pretty obvious from your graphs which one they are. So if I move this now so that it's at essentially, we're now at 10 degrees. What's nice is you can just move the book closer, although that's not going to work because it's actually falling off. As I said, the hard part is actually getting the angle correct, but it's the funner part. So reset, record, make sure everything's nice and 0. Stop. I think there might be an issue with this one, so I'm going to try that again. The reason why I think there's an issue is the IOLab actually lifted up the book for a second. That looks good. All right, so zoom on both of them. Highlight from the start of the velocity change to the maximum. I know that wasn't quite the maximum. List the maximum, looks like 0.601. 601, it'll have the same plus or minus for all of these. The time interval is 0.409, 0.409, which seems like one of these is probably off, but maybe I'm wrong. We'll see as we go. 4092, 02 seconds. Then to 20, and this is where things get a little harder because getting this thing up to 20 degrees. Reset. Record. So it should look nice like this. You should get a nice curve here. Highlight. Nope, that wasn't what I wanted. Highlight. Your data. So all we're getting is the time and the velocity. So the velocity is about 0.892. And the time is 0.27614. And the final one that I have here is going to be 30 degrees, which is even more of a pain. You might want to put something to keep it from moving. Still not quite 30. I need something to stop it. That's annoying. And you could do this on stairs or something else too. That might work. Or maybe even hold it with your hand. That might have to be. Why are you such a pain this morning? You worked fine last night. That was only 25. Maybe that edge is garbage. Nope. So I'm at 30 now. Was it 30? Yep. So go back to this. This is my 30 degrees, and you can tell that 30 degrees is huge. Make sure you catch your iLab. You don't want to let it drop and hit the ground. Zoom, zoom. Find the interval when it started to fall. This is 0.93, and we'll talk about your data in a second. 0.930, and my time was 286. So something's wrong between these two, and we'll see that. I'm going to leave them for a second. 28683, and we'll see that when we do our graph. So you're probably going to have to do this too. Remember, take theta times time. So 0.174 times 0.40902 is 0.0717, or 12, let's call that. Theta 0.348 times time 0.27614, and I get 0.096, and then finally 0.5236 times 0.28683, which is 0.150. All right, now that I have this, you need to do this in Excel. So I'm going to create a new Excel. The reason why you need to do this in Excel is I don't know how to do something that we need to do in Sheets. So if you can find it in Sheets, that's great if someone knows. But we're going to get the slope now. Going back to here, we can see that we want G to be V final over theta T. So we want to graph V final versus theta T, Y over X. If we do a linear trend line, we get Y is equal to MX plus B. This M will be V final over theta T if V final is on our Y, theta T is on our X. So, coming back to here and coming back to our data. Nope, don't want to annotate. Stop. Nope. Where's my data? So here's my data. Here's my graph. I want X and then Y. Remember, so our X is theta times T. That is 0.069, 609, 0.0712, 0.096, and 0.150. Then I want my V final, and that is 0.460, 0.601, 0.892, and 0.930. Now, first check here is your V final should have increased with angle, right? Because the higher up, the faster it's going to be going when it hits the ground. And theta times time should also have, or may not have increased, depending, because theta increased and time decreased. But as a first check, make sure that your velocity is increased with increasing angle. Then we're going to take that and we're just going to highlight it and insert. I'm going to do this like this, insert a graph scatter plot. Now we can see here that it looks like something went horribly wrong. This data point here, which is, first of all, theta times t, and this is, so this is v, this is theta times t. So this data point that's at 0.15 is bad. My final data point is garbage. I can see that because if I drew a linear slope, if I just drew a line, these three are on that line, that one's not. So knowing that, let me go back and redo that last one and see if I can do it better. So I need to go to 30. Such pain, but it is. So at my 30, record. Nope. So let me see if it's actually got a little bit better. So my V here is 1.092. I could zoom in if I wanted to. 1.072. 1.1. Let me zoom in on that a little bit. It's about 1.112, it looks like. So it's still not happy, and I'll tell you why in a second. 1.2, but my time, at least for, that's 0.356. 0.356, which seems a little bit 06. It's bigger than this one, which bothers me a little bit. But let's look at where the data lies on there. So theta times t is 0.35606 times 0.5236, 0.18, 0.1864, and changing this to 0.1864, changing this to 1.112. My data point's still way off. And that's because my time is off. So let me try one more time. Like I said, this is the part that really does kind of suck. Mostly because this thing has been quite a pain. You know what? I think I know what happened. All right. Let me start here. Again, we can zoom in to make sure we get exactly, we're not quite there, but 1.116. You can see that it's kind of a guessing game unless you zoom in really close to get the time totally accurate, but 1.116 was what it looked like when we zoomed in. Yeah, 1.116. And the time was 0.26068, which I feel a lot better about. 6068. And theta now is 0.5236 times 0.26068. 1365. Let's see if that actually gives us a much better, which I think it will. So 1365 and 1.116. So that's a lot better. You can probably play with it until you get it exact, but this is close enough for what I want to do. Make sure that on this chart you title it. Your axis should be V final meters per second over times theta, which is rad per second. Let's put a, where is it, chart design, add a chart element, go to trend line, add a linear trend line, which is just a line. We can see that that doesn't really look great, but that's okay. My R squared and my, I can see that this data set kind of sucks. Let me make this really big. So my R squared is pretty crappy. Now, this is V final minus, or this is, my slope is G, which is V final over theta times T. That should be about 9.81, right? And I see that it's 8.5559. And you might go, well, that's really far off of gravity. Well, yeah, but we have friction, and we're going to consider friction in a minute. But for now, this slope, this number on your X should be close to 9.81. It shouldn't be over. If it's over, that means that somehow physics made it faster. If I take out this, I get a much better line, but look at my slope. My slope is now greater than gravity, which means something's wrong there. That can't be. Go back through and run those tests again. So let's put this back. What was it? 0.1365. And this was 1.116. I don't want you fudging your data, but you might need to run it a few. And why did that? Oh, I know why that changed. 0.116. So let's say this is your data, and you've labeled the axes with units, and you've labeled the type. We have one more thing to do that we haven't done yet. So we have our trend line, and our trend line, I can write 8.5559, 8.5559 times X minus, my intercept is 0.0126, which is pretty good. But the error in the slope, how do we get the error in the slope? Well, Excel has a nice, fun way to do that. There's a video here that will take you through it. It'll take you to YouTube. You can watch it. It's something called the linest function. I will take you through how to do that. So first, somewhere off to the side, type linest. Linest has to be all capital. It's the linear estimate. Put a parentheses. Then you have to pick your y's. So just highlight your y's, highlight your x's, next. Highlight your y's, put a comma, highlight your x's, put a comma. Then put another comma. What this is normally if you wanted the slope to go through zero or the line to go through zero, there's something you can put in between those two commas and it will make the line go through zero. We don't want that. We want to leave that blank. Last thing you write is true. And this is all just computer talk or computer programming to do the linest function. Then highlight a box 4x4. If you come in here, this is where things get weird. You have to hit Control Command Return. Nope, that was wrong. Shift Control. Nope. I always forget. It's in the video. Shift command. Shift command. Nope. Control shift. All right, let's go to the video and watch it. Let me go to this video because I always forget that part on my Windows, and it's the most important part.
Today I'm going to show you how to do some quick and easy linear regression analysis.
This is what it's going to give you, and we'll get there.
With Excel. Outbrand, I'll post and the first thing I'm going to, so we're going to add loop and the error and the things that have to go into this function. The first thing is the Y values. So I'm simply going to select those and hit a comma to move to the next thing, which are the X values. This third thing is the constant. And basically, this is a parameter for setting your intercept equal to 0. We don't want to do that. We want to let the data decide where the intercept is going to be. So I'm going to leave that alone. And basically, I'll just put another comma in, leaving it blank up here in the formula. And that will set it to what it needs to be set to. We do want the statistics for the linear regression analysis. So I'm going to set this value equal to true and then close the parentheses and hit enter. Now what you'll see is that this gives us the slope. There's the slope, 1.6774, same thing here. Okay, now this formula, Linus T, is an array formula, which is maybe a little different than you've used before with Excel. And the way these work is that I'm actually going to select a large section here, and this is comprised of 2 columns.
Oh, that's what I
and 4 rows or 5 rows, depending on how you look at it. But this box here, and then I have to actually select in the formula bar here, and I'm going to hit Command Enter. As a Mac user, you would use Control Shift Enter if you're using.
Okay, Control Shift Enter. So I need to select a box 5 by 5. Then I need to go up here in the box, Control Shift Enter. And what I had messed up was I didn't select the array. Now what this is going to give you is, so he's got them labeled here. It gives you the slope. So the top one is the slope. The next one over is the intercept, and you can see it from his line. And I'll show you on mine in a second. This is the standard error in the slope. This is what we want, this second box right here. This is the error in the intercept, the R² value. I don't know what F and DF is, standard error in a Y. All this residual and regression stuff is stat stuff we don't need. But we do need this second box down. That is the error in our slope. So I have my slope is 8.5558, which as I can see is there. My intercept 0.02126 with a negative sign. My error of my slope is 1.2637. I'm going to call that 1.264. So here, I'm just going to write 1.264. So this is my theoretical gravity is 8.5559 plus or minus 1.264 meters per second squared. That is cool. You might actually need this for your bio classes or your chem classes or your later physics. We might use it once or twice more, but just so you know, this is Excel's way of giving you the error associated with a slope in a linear trend line. It doesn't work for others. I don't know what the functions are for those. So we've got this all filled out. You've got 4 nice trials. You've got your theta in radians. Your error of your theta is plus or minus half a degree. You have that converted to radians. So this will be the same on your lab. You have your final velocities at the bottom and the error associated with them, which is half the resolution of these numbers, which is half of the smallest digit. Your time, which is half of the smallest time that it gives you. And then t times theta. And then we graphed v versus t times theta. And we put a linear trend line on it with using linest, and we got the error of the slope. So that part's all done. I want you to, when you do your runs, your experiments, I want you to screen grab them. So in Windows, it's Command-Shift-5, and you just capture it, name it something. But make sure that you look at the Excel. So do this together, maybe if you can, on Zoom with someone, or if you're doing it on your own, put it into Excel before you're done experimenting, and check and see that you get a pretty nice linear set of data points. If one of them's way off, it's going to throw everything off. And your G should be somewhere less than 9.81. When I did it last night, I got like 9.5. But so you might have to do a few runs over. You might have a few that end up outside. So please redo them until you get a nice G. The video is here. If you need to know about LinEst, watch it again. Now, what are we calculating? We're going to calculate G experimental. So we're going to go back to our data set, and we're going to calculate from this right here, our experimental G for each of these trials down here. So put the angles again in radians. You can just copy and paste from the data table. I can just copy that, paste it. But G experimental, I need to take V final over theta T. So V final over theta T. So I would get 0.460 divided by 0.0609. For this one, I get 7.553. 7.553. Units are already there. My delta G though. So this function depends on V final, theta, and T. So I need to take the partial of each one. These should actually be, yeah, I need to basically find the percent error of each one. So delta G over V is, if I take the derivative of this with respect to V, I get 1 over theta T. I multiply that by the experimental uncertainty of V, that 0.0005, divide by my experimental value, 7.553. Do that again for each one, and you get this. So basically what you end up with is this right here. 0.0005 over G, or over V, so 0.00005 over 0.460. Oh, so we can do this. This is all I expect to do. Copy and paste all of those here, but then copy and paste again the final equation here. Copy. Why are, oh, because it's trying to do the header, huh? Now, my delta V was 0.005. 0.005, was it? 005 and 460. And 0.460. My delta theta was 0087. And my theta was 0.087. Is that correct? Guess it is. Weird. And then my delta T was 5 times 10 to the minus 6 over 0.7. Over essentially. Oh, and I'm dumb. I just wrote that up here and I shouldn't have, but okay. Copy. Paste. And so you can just plug those numbers in here. I shouldn't have plugged them in here, but I'm not going to go back and fix it. Paste, and then doing this, I can see that I get 0.0005 divided by 0.460 times itself. I get 1.18 times 10 to the minus 6. 1.18 times 10 to the minus 6. 0.0087 divided by 0.087. I get 0.1 times 0.1, I get 0.01. And this one ends up being 0.00005 divided by 0.7. And then square that. And I get 5.1 times 10 to the minus 11. Now, this term is times 10 to the minus 6. This term is times 10 to the minus 11. Pretty much our answer is going to be right here, and it ends up being 0.1 times 10% or times 100%, which is, there's an error in G of about 10%. It's about a 10% error. What it comes down to, what you're going to notice when you do these delta G's is all the error is in our angles. It's because our protractor has a resolution of 1 degree and we're doing 5 degrees, 10 degrees, 20 degrees, 30 degrees. So we're going to have all this error due to our protractor. These terms are virtually completely known, completely 100% accurate, which is really good. But all the error is going to come from there. Then I want you to find the percent error with gravity. So we found, oh, and I should say delta G ends up being something like 10%. Okay, so I want your trend line again. I want your experimental gravity. So what was our experimental gravity? 8.5559. 8.5559. If that's right. Did I put too many fives? No, just enough. Do the percent error. So subtract 9.81 minus 8.5559. Divide by 9.81, multiply, I get, this is about 12%. It's 12.8% actually. That's pretty high. And you might go, wow, that's not even close. Well, don't worry about this part just yet. We'll get there. We neglected friction in our answer, and we're going to find friction in the questions. So yeah, your percent error might be good, might be bad. Last night, mine was really good. Today, not so great, but you could see on my graph, it's gone, that some of my data points really weren't on that line. So I probably wasn't as careful as I should have been. So be as careful as you can. If you can get 4 really nice linear data points, you might get a really close value to 9.81. It just depends on how careful you are. So our questions. Okay, so I want the 4 screen grabs. I want the graph of velocity versus data times time, linear trend line, all that good stuff. I want the data table done. I want these calculations done for only the first one, but you're going to need to do all of them for, all 4 trials, right? And then trend line and do that. In the questions, we assume the ramp was frictionless. I want you to draw the free body diagram like I did here, like I did. So this free body diagram here with friction. Draw the free body diagram as if there was kinetic friction and use A is equal to V final, and give the acceleration in the x direction if there was kinetic friction. A is V final over T for the acceleration, not G. Solve this equation for the coefficient of friction. So what I'm saying is you're going to have your equation for friction here. We're going to plug in for A, V final over T is equal to mg sine theta minus mu n, but n is mg cos. I can cancel all my m's, and I want to solve that for, where did you go? I want to solve this for mu. So mu is equal to g sine theta minus v final over t divided by g cos theta, right here. Okay. Notice, let me actually rewrite that for a second. So we got that MA was MG minus, MG sine theta minus mu MG cos theta. We want to solve this equation for mu, but we also want A to be V final over T. Cancel all the M's. V final over T is equal to G sine theta minus mu G cos theta. Solving for mu, move that over, divide through by G cos, G sine theta minus V final over T, divided by G cos theta. Now, on here, I want you to, for the first and last, so for the 5 degrees and the 30 degrees, I want you to find the coefficient of friction using, from your data table, V final and T, and the angle 5 degrees, and then G is 9.81. So this would look like for me, my V final for my 5 degrees is 0.460 and 0.7. 0.460 and 0.7. So mu would be 9.81 sine of 5 degrees minus 4.60 divided by 0.7 over 9.81 cos of 5 degrees. And what I get is 9.81. Make sure my calculator is back in degrees. Sine of 5 minus 4.60 divided by 0.7. Divide that whole thing by, and y is at negative. 4.60 divided by 6.50, 9.81. I forgot something. One of my signs is wrong. So that comes over and this goes over. Shouldn't be negative. I think I forgot something stupid. Oh, yeah. Thank you so much. I'm like, there's no way this thing should be negative. That makes no sense for a coefficient of friction to be negative. It's 0.460. Yeah, that makes a lot more sense. So 9.81 sine of 5 minus this answer is 0.978 whatever divided by 9.81 cosine of 5. And I get 0.02. Very small coefficient of friction here, which is nice. But essentially what this is saying is this is what the acceleration is expected to be, g sine theta. This is what the acceleration actually was. So when we subtract that, we get the true acceleration divided by g cosine, which is the normal force. And so that is our coefficient of friction. It's very low, very small, but it was enough to slow down our iLab a little bit and make it so that G wasn't exactly, our G experimental was 7.553, which is a lot. That's a lot of friction in the affecting the system. We can do the same for this one. It would be G sine of 30. So let's do that with our data here. We would get 9.81 sine of 30 minus V final 1.116 divided by time 0.26. I get 0.6127. Divide that by 9.81 times cos of 30. And I get 0.072. Now, that's weird. So I got 0.02 for 30 or for 5, and I got 0.072, almost 4 times greater for the coefficient of friction was 4 times greater at 30 degrees. And what you should see when you do those, if you did all of them, is the coefficient of friction goes up with our angle, but what else goes up with the angle? The velocity. So the friction is either air resistance, which is dependent on the velocity squared. So the faster the velocity gets, the greater your friction. Or maybe the friction in the wheels of the IOLAB is dependent on how fast they turn. So the faster they turn, the more they slip and slide around and you lose acceleration. It could be a lot of things. So what I'm asking you to do is find mu for using a free body diagram and symbolically find mu. And then here, I want you to assume there is friction, and I want you to find the value of the coefficient for the smallest angle and for the largest angle. And then explain why you think they're different. Why is it increasing? I gave you a couple answers. You might have better answers than me. So that's it for the questions. The independent variables, remember, are the variables that we control. What did we control in this lab? We controlled the angle of the ramp that we were sliding down. The fixed variables are something you cannot change even if you wanted to. The only fixed variable is usually gravity. We can't control what gravity is. It's 9.81 meters per second squared. I mean, we could move the lab itself to a different place, but generally fixed variables are ones that you can't change. A fixed variable might be the density of water. While technically you could change the density of fluid, you couldn't change the density of the water. And then dependent variables are the measured variables, the things that we're looking for. We were trying to find the velocity, the time. Those were both things we measured with the IOLAB. We were also measuring experimental gravity. So those are all. So in the conclusion, please write an essay. Just don't include these in your conclusion. Write the essay, but address these 4 things in your essay. How good was our data? So give your experimental G, give the percent error versus the theoretical, talk about whether it was accurate or not. My 8.55 versus 9.81, probably not great. Pretty far off from what it should be. Why? Because of friction. State your uncertainties. So make sure you give your uncertainties and your experimental acceleration, your y-intercept, your r-squared value for your graph. If you looked at mine, my r-squared value was terrible. It was like 0.95. Needs to be over 0.99 to be good. So my data didn't really match a linear trend line. Yours hopefully will be a lot better. Are these errors small enough to claim your experiment was accurate? Well, maybe. And remember that the y-intercept value on your trend line is a measure of the systematic error. We didn't do enough random trials to get rid of random, but we can assume that there's a little bit of systematic error, but look at how small my systematic error is. 0.0126 is pretty tiny. That change is nothing. So it's like what, 1 part in 850? That's really nothing. So I have a pretty accurate experiment here, at least for the linear, even though r-squared isn't great. I know that whatever systematic errors I had weren't affecting it too much, it doesn't look like. What kind of errors were there? Air resistance, friction with the surface, friction in the wheels, lag in the experiment, meaning that the data transferring to my computer might have had some lag, so the timing might have been a little off. There is human error. Let's not talk about that. But which of those is systematic, which is random? I'm going to go with they're both kind of random because of the way the IOLAB maybe responded to the air and the surface. The surface I used wasn't uniform, but you can justify them as either random or systematic. It doesn't really matter. It's up to you. There may be some systematic error in how the IOLAB judges time. I don't know. There may be systematic error and lag between what the IOLAB's doing and when it gets to the computer, so that could lead to a little bit of of error there. It's really up to you. And then how do you take this to the next step? I obviously used a book, so I only went 12 inches. You could do real ramps. In fact, you can if you want. If you have some real nice long flat plywood or something around your house, or somewhere that you can actually judge, that you could actually move the angle, you could try this with longer ramps, assuming you can take your computer out if it works on your laptop or something. I don't know what other next steps you might want to try. You could do Galileo's thing. You could actually get your partner's IOLab and put some weight on it and see if the heavier one or the lighter one goes down first. I don't know. There's all sorts of fun things you could do with this. But the main idea of this whole lab is to get you comfortable with friction. I wanted to teach you about the lin-est function in Excel, and obviously, doing a little bit of actual experimentation with the IOLab and seeing kind of what it can do and where the error comes in with it. It's not great. You might get better. One thing I would do, you can actually try aluminum foil, wrap your book in aluminum foil to make it essentially frictionless and see how well it does, if it does better. But yeah, I don't think this lab's super hard. It's actually kind of fun. Everything's given to you. The friction part's a little weird, but it's all broken down here for you. And yeah, hopefully you guys have fun doing it. So remember, this lab report's going to be due on a week from Sunday. So you can put this away until after the exam. Do it next week. I don't care. We'll have another lab a week from Thursday. Next week, we're going to have on Tuesday, Chapter 7, and the president of IBC is coming to class. I don't know why. I don't know how long. I don't know what he's going to talk about. So hopefully it's informative and nice, and you guys will get to meet him. He's a fun guy. I got to see him at the faculty meeting. He's a blast. He's a really nice guy, and he probably wants to talk to you all about getting back to class and appreciating all your hard work and staying with classes. Our test is on Thursday. It's a take-home test. It will be available at 11 a.m. When you go through it, you can print it out, write your solutions, and then scan the test back. You can write your solutions by hand on paper. Just make sure you tell me like question 1, part C. And you need to get it back to me by Friday at midnight. But I will be here during class from 11 to 2 as normal on Thursday, and you'll be able to ask me questions in person. After class is over, you can text me or email me, and I'll try to get back to you if you have a question with it. I honestly believe most of you, it will take an hour and a half to do. I hope maybe 2 hours if you're taking your time. It's not meant to be hard. It's 4 questions. It's a lot like the practice exams. Things that aren't on it. Uniform circular motion isn't really on it. There's none of the velocity addition stuff. There's none of the vector stuff. There's not a lot of crazy like trig formulas and stuff like that on it.
Is there extra credit?
There is only one piece that's extra credit, and I'm not going to tell you what it is. It's out of 165 points, and the extra credit's 10 points. So whatever that is, that'll add. Well, that's like 6%. So there's 6% extra credit. My theory on extra credit is it's really there for the people that are really good, that blow through the exam and maybe inadvertently screw up somewhere so that they have enough points to cover anything they might have done wrong, any points they lost. But remember that 90% of the questions, if you look at the practice exam, are really setting up, doing free body diagrams, writing the right equation, and knowing the variables. The actual calculation with your calculator isn't a big deal. I will say that question 3, I believe, yeah, question 3 has some weird stuff in it. So I will be here Thursday and I will explain question 3. It's something that we haven't really seen before. I don't want to say any more than that. I'll talk to you about it on Thursday. But if you can do the practice exams, you're fine. If you get the practice exams, you're going to be fine. I don't want you working together. I don't want you consulting other people. I want you to do the work on your own and do your best. And if you get stuck, take a little bit of a break and come back to that problem later. Sometimes you just need to let your brain think things through. You have the opportunity having 2 days to kind of think about them. And I think you're going to find the test is probably easier than you think. Most of what I want to see is that you can do free body diagrams, that you understand how projectile motion works, how to write the equations and then use them together, the x equations and the y equations, how to write, you know, how to understand constant acceleration equations and stuff like that. There's, it's pretty straightforward though. And I honestly think if you've been doing your homework a lot, like Lucas and some of the other people that have talked a lot with me about problems, you're probably going to find that it's pretty straightforward and easy. If you're behind, yeah, you better get on it. I think it's a fair test. There's not a bunch of stuff coming out of left field. There is one thing in problem 3 that's a little out of left field, but it wouldn't be a test if there wasn't something weird in there, right? To make it interesting. So I'll see you guys on Thursday at 11. And I don't want you to worry about the test. I want you to think about it as an assignment that you have plenty of time to knock out of the park, right? Yeah, so I'm gonna make sure and put the lab open. And then, like I said to Lucas, whatchamacallit, I'll try to get the homework for chapter 7 up Sunday night. And I think that's it, unless anyone has any review questions. I still do want to talk to you, Cole. I'm gonna actually stop recording right now.